Okay, welcome everyone. So we have defined what it means for two matrices A and B to be similar. And then we've proven a really nice theorem that if two matrices are similar, then they have the same characteristic polynomial, thus they have the same characteristic equation, thus they have the same eigenvalues. And so we were looking at a 3 by 3 matrix A, where the first column was minus 13, 12, and 24, and the second column was minus 8, 7, and 16, and the third column was minus 4, 4, 7. And now let's say we want to find the eigenvalues of this matrix A. Well, I can certainly go ahead and try and calculate the determinant of A minus lambda I for this 3 by 3 matrix, which if we use the cofactor expansion across any row or any column, we can see this matrix A has no zeros in it, so the cofactor expansion is going to be pretty complicated. But recall, what we do know about this matrix A is that it happens to be similar to a matrix B, which is a diagonal matrix that has the entries minus 1, 3, and minus 1 along its main diagonal and zeros elsewhere. So we can find a matrix P, which in this case is this 3 by 3 matrix where the first column is 1, minus 2, 1. The second column is 1, minus 1, minus 2. And the third column is 2, minus 3, 0. So that when we take matrix A and we multiply on the left by the inverse of P and on the right by P, that gives us this diagonal matrix, which is B. And now what's really nice is we have proven that for triangular matrices, and a diagonal matrix B is certainly a triangular matrix, that the eigenvalues of matrix B are just going to be the diagonal entries. So we can see right away, without calculating a determinant, without needing to solve a characteristic equation, that the eigenvalues of B are minus 1 and 3, where minus 1, the eigenvalue minus 1 has multiplicity 2. And since I know that A is similar to this matrix, that tells me, therefore, that matrix A also has eigenvalues of minus 1 and 3, where the eigenvalue minus 1 has multiplicity 2. So this is super nice, and this is what we're going to discuss next in more detail, which is, well, great, how can I find such a matrix P so that when I conjugate A by the inverse of P and P, we can find a really nice diagonal matrix B that's going to be real easy for us to identify the eigenvalues of that matrix. So let's consider two statements before we end this video. The first is saying if two matrices are similar, then they have the same eigenvalues. And the second statement is switching the order of these conditions, which is now saying if two matrices have the same eigenvalues, then the two matrices are similar. And so this first statement, if two matrices are similar, then they have the same eigenvalues. We know that that is true. So this we've proven with a theorem. So this is definitely true. The question is, well, what if we change the order of these conditions? Namely, if two matrices have the same eigenvalues, does that imply that those two matrices are similar? And the answer is no. So this is not true in both conditions. These are not equivalent statements. It is possible for two matrices to have the same eigenvalues but not be similar with each other. And so here is an example below that the matrix, 2 by 2 matrix, where the first column is 1, 0, and the second column is 0, 5, this matrix has eigenvalues 1 and 5. And here's another 2 by 2 matrix, which is 1, 0, and 1, 5. It also, because it is a triangular matrix, upper triangular in this case, it also has eigenvalues 1 and 5. We haven't discussed yet how to show that two matrices are not similar to each other, but these two matrices are not similar matrices, yet they have the same eigenvalues. So we can show that this statement is false by providing a counterexample. And one more caution before ending this video, and that is we've discussed the idea of row equivalence of two matrices. And we say that two matrices are row equivalent if performing a series of elementary row operations on one matrix, we're able to transform it into the other matrix. So similarity is a total different property of two matrices. So for example, these two matrices above, these 2 by 2 matrices, they are row equivalent because I could take and say 1/5 minus 1/5 times row 2 plus row 1 to replace this one, and we could get a 0 above this pivot. So these two matrices are row equivalent, however, they are not similar matrices. So similarity is a totally different condition that relies on finding some matrix P so that P inverse times A times P gives us the other matrix B back. Row equivalence is based on whether or not we can perform elementary row operations on one matrix to rewrite it in the form of the other.